We're starting now the chapter 2 of Pure Math 3, and one of the things we need to talk about is the exponential function. But I want to start recalling something that you've learned last year. Remember that topic about progressions? You had to study linear progressions and geometric progressions. One of the characteristics of geometric progressions, if you remember, is that it increased very rapidly or decreased very rapidly as well. Here, the exponential function, it works the same way with a very big difference. The difference is that last year, the domain that you were using were the natural numbers. You could substitute the expression by values of n that range from 1 to 2 to 3, etc. Here, x can take any real number. So now this is going to be a continuous function instead of points in a graph. All right, everything else is pretty much the same. So the exponential function is a function which has the variable as the power, represented here by y equals a to the power of bx, in which a is the base of the exponential and b is the coefficient of x. Can take any value, both a and b. Let's see what is the effect of changing the base of an exponential function. I think that you can get this without even recurring to the graph, but let's put it anyway. So I create here a little table for these two values, 3 to the power of x and 2 to the power of x. I just plugged in here some random values for x, ranging from -3 to 3. Actually, all the values here that are smaller than 0 on this little sketch that I've made, they are too tiny to plot. All you need to know is that they tend to 0 as you go this way by substitution. So go from 1, 1/2, 1/4, 1/8. In this case, 1/27. They get very, 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 very closer to 0 without actually ever reaching the value of y 0. Over to that side, as x increases, obviously the function is going to increase as well, but this one with a higher base will increase more rapidly. So all things being equal, a higher base will make the exponential function increase more rapidly. Increase only when the base is positive, because if the base is negative, what is going to happen? Look over here. Not if the base is negative, sorry. If the coefficient of the power is negative, what is going to happen? Here you have 2 to the power of x compared with 2 to the power of -x. So you remember last year when we were talking about transformations in functions, if you multiply the coefficient of your variable by a negative number, more precisely by -1, what is the effect of that? The effect is that you're going to have a transformation which is going to be a reflection on the y-axis. The same thing must happen here, since this is also a function. So what is going to happen? If you will know that just plotting the points would yield the same result, that's what I did here anyway. Obviously, since 2 to the power minus x is the same as 1 over 2 to the power of x, as the denominator gets bigger, as x increases, the value of the function gets smaller. And this is what you get if you compare both functions. One is the reflection of the other on the y-axis. Finally, if you compare now 2 to the power of x with -2 to the power of x, now we are multiplying the whole function by -1. And also, last year you've learned that doing that will make now a reflection not on the y-axis, but on the x-axis, right? So the values that you will get as you change x are going to be the same as you had before, just with a minus behind it. So this is basically going to do this to the graph. It increases, but on the negative side of y. So the reflection on the x-axis. It's important that you have an idea of changing the value of a and b thus to the shape of the exponential function. and that's the reason why I showed you this to begin with. As you can see on any of these, an exponential function has a very obvious consequence. Look at these values over here for 2 to the power of x. If you try to plot these points, and I only did for something that ranges from -3 to 3, you have values that are so different on the y-axis that range, in this case, from 0.125, that's 1/8, to 8. It is very hard to plot on the same axis, on the y-axis, these different values. So you have situations in our everyday life and in nature that are that can be plotted in with an exponential function, but are very hard to analyze if you try to plot them on a graph. So one way to get around this is by using what we're going to study now, which is the logarithmic function. Let's see what this is. So you're starting here with an exponential. A to the power of x equals y. It's just what you had there, but inverted the order. So if this is true, then you can say that x is the logarithm base a of y. Again, x equals the logarithm base a of y. This probably doesn't tell you much. So I want you to think of this every time you say this or you write this. I want you to think of this the way I'm going to say now. Think that x is the power that a must have so that the result is y. Again, x is the power that a must have so that the result is y. Let's see with an example. Never mind this part over here. Just in terms of reading in your head what you have over here. 4 equals logarithm base 3 of 81. What does this mean? It means that 4 is the power 3 must have so that the result is 81. 4 is the power 3 must have so that the result is 81. See? These values, you can get them with a calculator. I have here just a random calculator, the kind that you can take to your exams. And you have different logs over here. This will depend from calculator to calculator. The most general one, I'm going to try to show you over here, is this one over here. This one over here, you have log, and then you have the ability to put the base underneath and the value that you are logging in front. Then you have another one that in this particular calculator is here on top of this button, which is just log with nothing else. And then you have the ln, which I'm going to talk over here. It's also a logarithm, and I'm going to talk about this one later on this chapter. This one, the first that I mentioned, you can actually plug in the base of the logarithm. The other two have a standardized base. If you just see log, L-O-G, or in some calculators just LG, this means that automatically the base is the base 10. The ln, on the other hand, has base e, and you'll know what e is later on. So let's look a little bit more to the base 10, okay? As you know, 10 is a very important number. We have 10 fingers, we use a decimal system, etc. And let's see how these things relate with values that you know for a long time. So think of all numbers that go from 1000 to 0.001 to 1000. You can write this in powers of 10, right? Can go from 10 to the power of 3 to 10 to the power of minus 3. So how can you use logs over here? Log of 10, log base 10 of 1000 is 3. What does this mean? This means that 3 is the power 10 needs to have so that the result is 1000. 2 is the power that 10 needs to have so that the result is 100. Minus 2 is the power that 10 needs to have so that the result is 0.01. Maybe this is not obvious yet, but think of it this way. Imagine that you want to plot points that range from something that goes until 1000 to something that goes to 0.001. Actually, the other way around, that range from this to this. If you try to plot this on a graph, you physically have no possibility to plot at the same time something of this scale and something of that scale. The order of magnitude of 1000 as compared to 1000 is 1,000,000 times bigger. So there's literally no way that you have a paper in which you can plot these values. So what do the logarithms do? They enable you to plot by these values by doing a mathematical trick if you want. So now, instead of having 1000, you have 3. Instead of having 0.001, you have -3. So you have something that ranges from -3 to 3, only 6 units. See the thing here? You can now plot this in a paper. But you may be thinking, what kind of stuff ranges just like this? Well, most likely you studied science, namely chemistry, and you know the pH scale, right? It measures the acidity of a solution, and it ranges from the very little, literally close to 0 and up until 14, and this is a logarithmic scale. It measures the concentration of H plus ions, and it basically means what? Every time you go from whatever pH to one value above, so let's say from 6 to 5, the acidity of the solution is not increasing by 1 order of magnitude, is increasing by 10, because it uses a logarithm base 10. Every time you go from one value to the next one, the power, so to speak, is increasing 10 times. Another example is the scale that is used to measure the intensity of earthquakes. Either the Richter scale or the Mercalli scale, they are logarithmic in nature. So what does this mean? If you have two earthquakes, one scaled at 5 and another one at 6, the 6 is 10 times as intensive than the 5. So here you have examples of logarithmic scales. If you think of anything that is exponential in nature, you can think that the logarithm can be used to analyze data that is coming from that. I'm thinking of the growth of cells in a petri dish, for example, the growth of a disease like in a pandemic is exponential in nature, as we unfortunately know. In some businesses, the growth may be exponential. So you have numerous examples in real life in which the exponential function can be used, and therefore the logarithmic can be used to analyze this information. Like many other things in math, logarithms have their own rules that you need to know. First of all, and I'll start with this, logarithm base a of a equals 1. What does this mean? If you are trying to get the logarithm base whatever value of that value, this is going to be 1. Think of it. What is 1? 1 is the power a needs to have so that the result is a. Makes sense, right? 3 to the power of 1 is 3. 1000 to the power of 1 is 1000, so forth and so forth. So this is a basic rule. Similarly, if you have a to the power of logarithm base a of x, this is going to cancel that. So this is just going to be x. Logarithm base 7 to the power of logarithm base 7 of 3 is just 3. Then you have the rule of multiplication. If you have the logarithm base a of a product of two things, this is the same thing as having the logarithm base a of one of the things plus the logarithm base a of the other thing. Similarly, for the division, the same thing happens, but now with a minus, is a subtraction of the two logarithms. If you have now a logarithm base a of a to the power of whatever number, then this is equal to that number times the logarithm base a of x. There's a particular case here. The logarithm base a of 1 is 0 again. Just think of it. Well, 0 is the power a needs to have so that the result is 1. Whatever a is, if you want to find the value that powers that to yield 1, that value is only 0. 1 million to the power of 0 is 1. And this is true for any number that you can think of, with the exception of 0. These two are basically variations of the previous one. So you can write the nth root of x as x to the power of 1 over n. So you're basically here are just applying that rule over there. And here you are just applying this rule over here. This is logarithm base a of 1 over y. So if here x is 1, you'll have logarithm base a of 1, which you already know is 0. So it's 0 minus logarithm base a of y, which is basically minus logarithm base a of y.